Hello, my name is Andrew Brooks. This is Nonlinear Existentialism, Dynamic Amplitude Modulation, and the Central Limit Theorem, and also Maintaining Continuous Uncertainty. The reason why I'm giving this presentation is just a follow-up to the last presentation, just to give more detail on the relationship between nonlinear existentialism and central limit theorem. First thing to do is just giving a better schematic of what the FAM processing unit is like. You see on the left-hand side the 3D FAM unit, one FAM unit, and on the other side you have the 2D representation of three FAM units. The important thing to understand with this one is that it is a fusiform type of nerve cell, and as a fusiform type of nerve cell, you have a volume that not only has the axon in the middle, but also you have the neurites which fill in the volume. And the importance of this is that the neurites that you'll see on the right-hand side, well, you have a better view from the transverse, is how they interact and how, which we'll show later on, how they emanate from the axon, the neurites do, and how they tend towards the middle section, the parallel to the cortical layers. The important point with this is going to be the interaction between the axons and the neurons. On this one, what we have here is at the top is that we have the axon, but basically in its normal state is that it's going to have a certain negative charge inside because of the ion channels. They're going to be removing more positive and having more negative come inside. So what we're going to have is resting potential is going to be negative. And part B here is when you're having your normal all or nothing activation energy. We're going to have is what starts on the left hand side is going to continue on to the right hand side. So there's not going to be no energy decay. On the bottom there, you have the neurite. It's small in caliber and unmyelinated. At the top, the axon, which is a larger caliber, it is myelinated. The important thing to realize with the neurite, sorry, is there's no channels, and the passage of any um, electrical charge inside the body is going to be just relatively passive. So there is going to be energy decay. The important thing to realize with this, and this harking back to the originating paper on the subject, is that we have is on the main neuron, as you can see through the oblong tapered at the top and at the bottom. What it happens is that it goes down the primary pathway, which is the axon, and it bifurcates at area A, and you're going to have a secondary pathway and also a primary pathway. And at the bottom B, they come back together, and based on the timing between the two, they might add or they might subtract or just stay equal. And that's where you're going to have basically the idea of the amplitude modulation. But it's at this stage it's also very important to get in more detailed steps in axon neurites and modulation. Basically, what you have first is going to be the input. You have the flux of energy states surrounding the nodes of Ranvier. And you can see on this one what I'm referring to is at the bottom there you're going to be, for example, thalamic cortical input. And what happens is that it's going to be going towards the top of the cortex. At the bottom is layer 6, at the very top is layer 1. And as it goes up the non-myelinated axon in the nodes of Ranvier, which are shown as the lines, we're going to have a charge around them. And this charge in number 2 is going to be interacting with the neurites, which are going to be in parallel to the magnetic field which is going to be developed. That magnetic field is going to cause a frequency modulation, but also at the same time it's also going to be causing the neurites to grow towards it, so it's going to be actually changing the length of the pathway. So you can review this in this one where we have the number 1 is input, thalamic, cortical, and other cortical projections. Number 2 is going to be flux of energy states surrounding the nodes of Ranvier. Number 3, excitation of unmyelinated contiguous horizontal components of layer V1b of the cerebral cortex. And that's going to do the production of electrical current based on the caliber of the neurite. Again, this is passive. Production of a magnetic field emanating from that layer. Neurite movement towards the center of the field, and minute change in length in the neurites. And this is important that leads to basically continuous uncertainty, which we'll discuss later on. Anyway, step 4, what we have up there is that it's once we have the energy transformation of input patterns, you're going to be going back towards the lower cortical layers. And when that happens, it's split into primary and secondary pathways, as was discussed before. And as you go, number 6 and number 7, talked about that before. And then we basically also going to have frequency modulation. The frequency modulation, as I mentioned, is when you have the emanations from the electrical current. You have the magnetic field. The magnetic field is going to basically set up the frequency modulations, which will, as mentioned in previous papers, give the concept of a binding and also of a shared time frame. So with this one, what we have is we've already discussed the ideas of frequency modulation, how they relate to amplitude modulation. Of course, this is just a very quick overview of this. What I wanted to put that, just put it in the frame of what the FAM processor is about. FAM being frequency amplitude modulation, how they relate to each other and how it occurs, because it's very important to have a physically bound and detailed composite overview of what the FAM processor is and how it can possibly do what's been discussed before. But with this one, I would relate to the idea of the central limit theory and a static amplitude modulation. What we have here is just a very quick overview of what a central limit theorem is. Central limit theorem just goes in the idea that you'll have the normal statistical bell curve that we have in front of us, where the MO is being your average, and you have your statistical deviations from the average. In order to adhere to the central limit theorem, the variable which is going to be mapped on by this has to be continuous, independent, and random. And at the bottom here, what I've mentioned is the percent probability of change input amplitude in individual FAM units is where you have it is being static. The idea is that if you've got all these different configurations in the neurite volume that was shown on the previous slides, is that they're in almost a in a large number of configurations that can almost be in any type of configuration. What you basically have is that you almost have every different type of permutation. So you have a large interaction of these neurites, which can be almost in any formation, which makes them basically contiguous. And because each one of them does not determine the other one, they are independent also because their setup is due to independent processes which are not set, then they are random. Based on this, so that the configuration of the FAM process of the neurites themselves can basically be considered to be described in the central limit theorem, and therefore the percent probability of changing input amplitude in individual FAM units is going to be described by that too, and that's why we can say that there's a relationship between nonlinear existentialism as described by FAM and the central limit theorem. But the important thing on this one is that, as you can see at the very top there, is static amplitude modulation. If we step back and just say that the individual framework, the individual neurites as they are fashioned and described from birth, let's say in each neurite volume that is shown in the first slide, then we can say, well, maybe perhaps that because they are continuous, independent, random, they actually will give uncertainty. They will only give uncertainty up to a certain amount of time at first, because there's almost appears to be an endless display of change or differences in each individual neurite volume, and each one of the FAM processes are somewhat unique. But over a period of time, that they will come actually to that the pathways will be described, because each individual neurite volume is described as well. So the uncertainty we have is only because of set complexity. What we have here in dynamic amplitude modulation and central limit theory is the idea that each individual FAM units, because of the change in length, will themselves change and give almost an endless degree of continuous uncertainty. So but the thing is, because they are also still described by the idea of central limit theory, that when one neurite volume of certain configuration of neurites changes, it changes to something else, which you can see at the arrows at the bottom of the diagram. But then another one takes its place and back and forth until, even though they are changing, just given the idea of probability and such high numbers of FAM units, that the bell curve is still going to be evident and is still going to be described by the central limit theory. But at the same time, each individual units are modulating somewhat, so they still have a certain amount of uncertainty as described by central limit theory, because they have an average amount of uncertainty, let's say 0.02 for 2%. But because the configuration is changing somewhat, their 2% uncertainty is going to be ranging over a certain amount of permutations. So in the end, it's still going to be continuous uncertainty, even though you can step back and look at it and say that they are still being described by central limit theory. So in conclusion, FAM adheres to the central limit theory. It's continuous, it's a large number, it's independent and random. However, furthermore, because the cytoarchitecture of the individual FAM processing units is also in flux, the output of the system will continue to be uncertain. And that's very important because a lot of modeling systems that they use, they come up with the idea that the individual units, they don't call them FAM, they have their own processing units with different weighting. The weighting is more dependent, and what FAM is independent, and it gives the amount of flux that's necessary, but also at the same time it still adheres to central limit theorem, which allows to have an average amount of probability of change, and that's very important because without it, it becomes too chaotic. So if you have any questions, sorry for this brief overview, but I just wanted to clarify the association between central limit theorem and nonlinear existentialism, and also giving a little bit more meat on the skeleton of the FAM unit. And again, just reiterating what was said in the beginning paper that brought up these ideas that I'm just trying to flesh out in these presentations. Thank you very much. Take care and have a good night.